Hello, Raisin River. My name is Sebastian Belliard. I'm a soil management specialist with OMAFRA based in Kentville. It's a little awkward for me because I'm not actually around. This is a recorded presentation, but I'm happy to contribute regardless with a presentation on understanding and assessing soil health. Three general things I want to cover today. What is soil health and why should you care? How can you tell if your soil is actually healthy or not? And what can you do to make those soils healthier? What is soil health? There's lots of definitions out there. In some ways, I don't really care which one you use, but I like these two from Ag Canada and from the USDA NRCS for a couple of reasons. I like the fact that Ag Canada focuses us on crop growth, which I think is important because usually when we're looking at soil health and we're talking about it, trying to understand it, it's from an agricultural perspective, and that's important for some reasons that we don't need to get into, but keep that in mind. The reason why I really like this USDA definition, defining it as the continued capacity of the soil to function as a vital living ecosystem that sustains plants, animals, and humans, is for that focus on function. And I like that because it helps guide us a little bit in terms of what we need to be looking for, what we need to be trying to measure or understand to know whether our soils are healthy, and that's that function, those soil functions. So what are those soil functions? Well, there are some slightly different lists, but all the important ones are here. Things like plant production, crop growth, essentially in this context, matter cycling, things like breaking down crop residues and organic amendments and releasing those nutrients back into the system, creating a habitat for biological activity, things like worms, springtails, and fungi and bacteria, all those organisms that contribute to making the soil a functioning living system. There's the filtering and buffering of water. We know that the soil accepts water from the atmosphere and then filters it through, recharges groundwater, but also stores water and releases it for plants. And then there's carbon sequestration. We know that soil has a very big role to play in the carbon cycle and hopefully in carbon sequestration. So here's a slightly different list, but I do like this one. I'll bring it up because I like how it ties those functions back to our goals when it comes to farming, right? There's plant productivity, getting that yield, but also waste recycling, making sure that the system continues, and environmental protection, making sure that the water and the soil and the air that we actually depend on for our farming systems aren't becoming degraded. So how can you know if your soil is healthy? Well, like a lot of things, there are different ways of knowing. And I'll try to go through some of each of these categories, but I think it's important to note that you don't have to necessarily rely on lab tests or microbiologists or even soil specialists to get a sense of how healthy the soil is, to be able to tell, at least in some ways, whether your soil is functioning properly, if your soil is healthy, and what might be some of its limitations. So I'll try to go through some ways of knowing in each of these categories. I think the first one is the easiest. It's just experiential. Your experience as a grower working that soil year in and year out. There are things that you notice, things that in your experience of working that land that can tell you something about soil health. And so I've got here, a list of some answers from a SARE survey in the US a few years ago about, basically asking growers how do they describe their soils and how do they know if their soils are healthy. And so I've highlighted a few here that might be interesting. They said that their healthier soils sponged up and held more water, but they also dried out sooner in the spring. Their crop residues broke down more rapidly in the non-growing season. But also, kind of more indirectly, their fuel costs are way down. Their tractor pulls more easily as they go through the field. Maybe if you're lucky, your crop yields are higher as well. All these things that sort of fit in and come out of the soil system that you can use also to get a sense, kind of visceral sense of whether that field is performing well, whether that soil is healthy from an agricultural standpoint. Now, getting into maybe more robust assessment methods than, oh, this field feels nice while I'm driving over it. This is kind of what I call observational assessments. And I really think this is, in a lot of ways, this is the sweet spot, because you don't necessarily need to be a scientist or an expert to do these. Some of these might need a bit of training to sort of really get good and confident in them. But in the end, anybody here could do these soil health assessments and get good knowledge out of them. So I've got a list here of some that I've thought of. I'll go through some of these in a bit more detail, but things like crop performance, right? Like if the soil's healthy, well, it should grow a good crop. And soil structure is really an important one. Surface quality, percent residue cover, earthworm or earthworm midden counts, infiltration rate, how fast the water soaks into the soil, penetration resistance, how hard it is, is the topsoil nice and deep, and does it have a nice dark color? Are those roots growing the way they should to be able to get everything that they need? Are there symptoms of erosion that Kevin might have mentioned earlier? And yes, the underwear test. But I'd like to sit for a little bit with this picture here on the right, because I think it really illustrates the fact that, we can tell a healthy soil from an unhealthy soil, at least at the kind of extremes. We can all see from these two spadefuls which one of these is the healthier soil, right? Like, which one would you rather grow a crop out of? And that's pretty obvious. So let's get a little bit into the details. So one of my favorite evaluation methods is visual soil structure assessments. It's essentially what we saw in the previous slide, but with a little bit more rigor, and gives you a bit more confidence in actually being able to assess a spadeful of soil, to say, yes, this is a good structure, or like, no, this isn't as good as it could be. And really, to do that, you need a system. In this case, we're using the Visual Evaluation of Soil Structure, or VES, which is a system developed by some soil scientists out of Scotland, among other places, that we've adopted here. And I really like that it allows for that observation to be a bit more quantitative, a scale of 1 to 5, with a bit of interpretation in there as well. I think it's a really valuable tool to take into the field. If you want a bit more detail, there's a YouTube link on the left here, where I can take you through in video form how to use this, how in scoring a soil in Ontario. If you wanted to actually print out the PDF and take it to the field yourself, that second link should take you to a file that you can download and print for yourself. And on top of the fact that with just a little bit of training, everyone should be able to do this assessment, I really like soil structure as a soil health indicator, because it integrates all the chemical, physical, and biological things that make a soil healthy into one sort of key indicator, so that you know that if your soil looks like it does here on the left, with roots growing all through it, nice, very well defined, small, crumbly aggregates, then things are going well. Whereas if you're seeing what we've got here on the right, or even worse, something like this, then something is wrong, and you need to have a look at what might be causing that. One of the reasons why that good soil structure is so important is because of water. Having a range of aggregate sizes means a range of soil pore sizes, which means that the soil is able to both drain water more effectively, but also to hold on to more water in a way that makes it more accessible to plants. So not too tightly that they can't get at it, but also tightly enough that it doesn't just drain away. And you can see that here in this image of the optimum water range, which in a well-structured soil is much wider from being too poorly drained, too saturated to have enough oxygen for roots to grow, but also having enough water that we don't get to that permanent wilting point. Whereas in a compacted soil, that range is much narrower, because there aren't as many pores or gaps in the soil. Anytime that soil is saturated, there's no air left there for those roots to get oxygen from, and once it starts drying out, it very quickly gets just too hard for the roots to grow through. And this is a really good visual representation of that with a non-compacted soil in the left, where you can see nice big pores that are connected and continuous that go through the sample here. And once that's compacted, you see that really the first thing that disappears is those big pores, the ones that would channel water through, the ones that roots would grow through, and the ones that let those roots grow and breathe. And speaking of breathing, the surface of the soil has to be open enough for gas exchange to happen so that those roots can get oxygen to breathe and then also release the CO2 that they basically respire out. And it's the same thing for water also. If we're talking about infiltration, that soil surface needs to have open pores at the surface for the water to even be able to enter the soil profile at all, to be able to percolate through. And here's another kind of 5-point scale for assessing soil surface quality. Is it open? Is it protected by residue or living plant cover, or is it sealed and crusted and not allowing anything through? So what's happening when you see a soil that's crusted like this is that any rain that does fall isn't able to infiltrate, and so instead runs off, which means wasted precipitation and risk for erosion. Next, we'll move to counting worms, and I really like worms. I'm a big worm nerd. There's two different ways you can do this. One is just to actually count worms in a spade full of soil, so about 8 by 8 by 8 inches of soil, and actually sifting through it and counting the worms that you find. It doesn't work so well in the heat of summer when worms are hiding from that heat and the dryness. They might burrow deeper, they might be harder to find. But otherwise, you should be able to find at least 10 to 15 earthworms in a good sample. The other thing we can do for earthworms is to count middens. And so middens are these clumps of residue that you're seeing on the right picture here. That's all earthworm action. It's a specific kind of earthworm that we're counting there, those deep burrowing dew worms or night crawlers, whatever you call them. They have a really important role because of their deep burrowing action in maintaining soil functions. And I think after soybeans is a really good time to be counting those, because there's usually not that much residue on the ground, and so it's a lot easier to see the pattern there. You can see it a couple weeks after soybean harvest, where that nice spread pattern that you got out of the combine has started to clump up, and all of that is deep burrowing earthworm action, sort of creating a nice roof over their burrow to keep that microclimate and give them something to feed on. And so you should be able to find a good number would be 5 or 6 earthworm middens in a square foot sample. Here you can see, this wasn't a great soil sample, but I found 4 just in this. So in case you're thinking, 6 middens is a lot, I'll show you this video that comes from my front yard. And this is at night, because that's what you do when you're a soil nerd. You go and film worms at night. And then in the middle, you can see here what I mean by the really important role that they play in soil function. This is a poorly drained, very fine sandy loam. You can see that from the orange splotches there and the light gray colors, that this is a poorly drained soil. And so water doesn't really move easily through this soil profile. But if you look at this worm burrow that's exposed here, you can see that it is dark and enriched in organic matter, and it's just this big channel that's going deep down into that subsoil, that if you look at the picture on the furthest right here, you can see roots will follow those channels. Those are basically highways for roots to go down. They're enriched with that organic matter, they've got nutrients, and it's just the path of least resistance for those roots to be able to go down into a subsoil and capture the resources that are there, nutrients and especially water, that otherwise they wouldn't have access to. And worms work really hard for us in the soil. Sometimes, I think a lot of times, we don't give them enough credit. This is a picture that I'd just like to share because it just blew my mind. It was from a field that was recently leveled, and I think it had been filled in also. So there's no plant matter for those worms to work with, and so they were actually making middens out of small gravel-sized pieces of rock. This is some limestone, and you can see in the picture on the left here that it has that clumping pattern. I didn't believe it at first, but if you look at the close-up here, you can see that there's some worm poop, some worm casts between those rocks, and there is a burrow under there. So, you know, those worms are working hard for you. There are some things that you can do to make their work easier, and we'll get into that in a bit. The last thing that I want to say about these worms is just that that function of or that role of creating those deep sort of larger channels, those big macropores, it's such an important role in the soil that it is in every kind of soil there's something that fulfills that role. In this case, in the case of sort of coarser sands that worms don't like to live in because it kind of scratches their soft skin, you'll see ants, ant hills doing essentially the same thing, creating that porosity, aerating the soil, and creating those nice, those large channels and macropores through. I've even seen little pink crabs doing exactly the same thing in swampy mangrove forests. So really, those deep burrowing worms, I cannot stress enough how important those are for proper soil function. Now, root growth, I think, is one that is maybe a little bit easier to translate directly into, you know, crop growth and productivity and essentially yield in the end. But it's not one that I think we look at enough. But here are some pictures that to see what we don't want to see. The picture on the left here, you can see a root that's deformed and it's flattened because the layer that is growing in right here is just too compact. There's just not the space for that root to grow through. There's not the pores for it to grow into and still keep its shape. So it is suffering. That plant is expending more energy than it needs to, trying to force its roots through any crack it can find in the soil, and really not being able to explore and get resources from a larger soil volume. And then on the right here, you can see a soybean root growing into a compacted soil where you can actually see those layers, and you can see that those roots have gone horizontally, and when things dry out, that root will not be able to access the water resources that it needs to keep going. And really what we want to see, again, is that nice crumbly structure. This isn't a silty clay loam, but a piece that had been in perennial grasses for a long time, and you can see there's roots all throughout this. They are able to capture anything that the soil has to offer them. Now, penetration resistance, I think, is not one that a lot of people go for because they think, oh, well, I need a penetrometer, and what am I going to do with that? It's just going to lay around. But you don't need a penetrometer. You can really use anything to poke the ground. Here's a picture of my summer student, Anna, trying to get a soil probe into a soil that is obviously hard and has some compaction. So you can use a tile probe, you can use basically anything that's long and pointy. If you do get a penetrometer, what you're looking for is about 300 psi for the point where roots will really kind of give up the ghost and not really want to grow through that. They'll try to find a way around it. But it's important to look also for the depth of that maximum resistance, you know, where that compacted layer starts, and if you can, also push through it and see if there's a point where that starts getting easier to push through to get a sense of how deep that compacted layer is if you don't feel like digging. But the important thing there is well, my video is covering, but here we can see on the top an uncompacted soil where those roots are able to grow all the way down through. At the bottom, we've got a line here where we have a compacted layer, and really those roots kind of stop growing at about here, the depth of that compacted layer. So when things do start getting drier later on in the summer, they just don't have the roots where the water is to be able to grow through it. The underwear test is a fun one that a lot of people like. Basically, you dig in a pair of cotton underwear. It's important that they be cotton and not synthetic, and washed is preferable. Leave them in for 2 months, and what you want to see is something that you might imagine a younger version of yourself wearing. But really just having the elastics left. So all that cotton, all that organic material having been munched away by the microbes. And this is kind of a proxy for how well your soil should be able to work through crop residue. So in terms of analytical soil health tests, lab tests, there are some out there. I don't want to forget to mention soil fertility because, again, if we're talking about soil health in an agricultural context, it is crucial to have that soil fertility figured out first. And then organic matter is the traditional kind of best all-around indicator for whether things are going well in the soil. There are other indicators that we use. But I don't think I'll go into too much detail on these. They could take their own presentation. I'll just say that we are working this year on getting baseline values for a range of soils across Ontario for these different indicators to be able to use them and score them and interpret them a bit more usefully when you're doing soil health tests. And now really the important part is what can I do to improve my soil? So maybe you've done some of these assessments, you've seen that there's some things that could be better. So what can you do in terms of management practices to address those issues? And I think it's easy to boil down into principles that can be adapted to a certain extent depending on the situation and the cropping system. But really those are keeping it covered, minimizing disturbance, maximizing living roots, incorporating plant diversity, and integrating livestock, or at least their poo, into the system as organic amendments. And so when we talk about keeping it covered and minimizing disturbance, that's really letting that soil structure build and improve. It means less risk of crusting, better water and gas movement, and better root growth and exploration, like we mentioned earlier. And these are pictures from the exact same field, less than 10 feet apart. This picture on the left where there hadn't been any residue after the spring tillage, and it had started to crust. And then in the top right here, just 10 feet away, there was residue cover, and when I pulled that back, you can see that the soil underneath there, the surface was much more irregular. It was open. There was aggregation starting. There were worms there. It was just a much more active and open surface for that soil to function through. And I think it's easy to say, well, don't do any tillage and keep the residue on top, but we are in Eastern Ontario and we have a short season, and so we need to have that soil warming up and drying out early enough in the spring so we can capture those heat units and get planting. And it's true that in almost all cases, no-till soils will warm up and dry out somewhat slower, just because there's not the heat flux and evaporation out of those soils. These are figures from North Dakota and Minnesota, where they compared 4 tillage systems and sort of the average water content and temperature from thaw to canopy closure. And yeah, you can see that no-till was a bit wetter and a little bit cooler than some of the vertical till or the minimum tillage systems. I think it's interesting to see here that strip tillage really is in a lot of ways the best of both worlds. And then, you know, these there's a lot more granularity in this information, in this data, in terms of it's not the same for all soil types. The more clay there is, the more wicking there is from the bottom, and that again might be its own presentation. And I think it's important to consider the trade-offs here. You can see these tables from the Upper Midwest Tillage Guide, that on the left here, those E's are the structural impact, structural degradation essentially, and the dollar signs being the cost of running that tillage system. So no-till at the bottom with the lowest impact on soil structure and also being the cheapest to run. Strip till then being second lowest in terms of soil impact, but being a bit on the pricier side. and that impact can be estimated also from kind of the aggressiveness of the tillage. That's measured by the soil tillage intensity rating on the table on the right here. And again, my camera is covering part of that, but you can see that the more aggressive that tillage gets, the higher the tillage intensity rating, and what that means is higher chance for structure degradation and higher risk of erosion and other consequences. And it doesn't have to end there. There's still innovation happening in this space of residue management, because that's one of the primary reasons why we do any tillage. There's seed bed preparation, but also a lot of that is dealing with the residue to be able to get those conditions of moisture and temperature in the spring that we need for a good cropping season. So these are some photos from my colleague Ian McDonald, who profiled this system using a Lamoureux toolbar. I don't know what they call this machine necessarily, but it's basically just two sets of row cleaners, one behind the other on a toolbar. They just run that through the corn residue in the fall so that it creates a nice strip free of residue that can dry and warm up fast enough in the spring to plant some twin row soybeans. And you can see that this is a system that can work and has some promise. Some growers are taking that a step further and doing what they call bio-strip tillage, which really doesn't have any tillage at all, but using the action of cover crop roots to prepare that seed bed in the crop row that's planned for next year. Usually there will be some mix of winter-killed cover crops in that row, and then in between usually an overwintering cereal rye kind of thing, though not necessarily, but the idea being that you'll have kind of very mellow residue that will decompose quickly in the spring in that row where you're planting your crop, so that that's ready to roll when you're ready to plant, but you're still getting the benefit of maybe an overwintering cover crop where you don't need to have that strip free of residue for planting. And this might be because I'm a worm nerd, but when I think of disturbance, I always think about the worms. It's very clearly shown that the more disturbance there is, the more tillage there is, the fewer worms there are. And one of the reasons is because tillage buries crop residue, and the only thing that those deep burrowing worms eat is surface residue, crop residue that's on the surface. You can see this later in the season in cornfields. When there's no residue on the surface and there's still some worms there, they're basically starving, and so they're starting to grab the leaves, the lower leaves of that corn crop, and trying to pull those in because there's just nothing left to eat. And you can see again here in this picture in the middle the importance of those earthworm burrows for roots, for root growth. They sort of act as these conduits for root. This picture is kind of interesting because you can see there's a sort of a plow layer at the top that those roots were still able to kind of get through, probably horizontally, and then found that those worm channels to be able to shoot down through. Something that we don't always think of as a disturbance, but I think really does fit in that category, is compaction. Here you can see an NDVI image, so basically crop health from the Ohio State University. This is work from Scott Shearer and their group, and you can see right down the middle across the field where the grain buggy operator drove the year before, so still showing up in this year's corn crop. If you're a fan of country music, you know that the first pass of compaction does the most damage, especially regardless of the conditions, but in unfit conditions, 80% of your crop loss from compaction can happen at that very first pass. And so if we don't have a system for it, we can be trafficking a good 80% of a field in any given season. And while it's fun to talk about maybe more the equipment side of things, like central tire inflation systems or nice rubber, I really think the easier thing to do is just control where that traffic is happening. And there are good documented benefits to controlled traffic farming systems. And if modifying your equipment like you see in this picture is not something that you're willing to do, that's fair. But you don't have to do that to get the benefit. You can use the equipment that you have and an equipment replacement plan to sort of get at more or less a CTF system. You can call it semi-CTF, where as long as you can try to match the implement widths, or at least have those in multiples of each other, so whether that's like a 30-foot planter with a 90-foot boom, you can at least drive on similar tracks and reduce that area trafficked from 70–80% down to a good 30%, which is a huge improvement already. The last principle I want to focus on is maximizing living roots, and you might be hearing more and more about living roots, and there's good reason for that. They're really the drivers of aggregation, of building soil structure, not only by their physical impact, but also the fact that they are feeding the soil food web, feeding the biology that's then contributing to that structure building and aggregation. And also having those roots in contact with more soil builds those interfaces where soil organic matter can start to be increased. And I think this is an important thing to note also when we're looking at the success of a cover crop. You might not be impressed by the top growth that you're getting, but I can assure you that even with not a lot of top growth, there's usually more root growing beneath that, and it is having an impact, as you can see in these two pictures. And I think we'll skip this interesting close-up of root cross-section. And we can see the benefit of all of those roots in this meta-analysis of studies on cropping practices and infiltration, where we can really see that the practices that most improve soil infiltration, water infiltration into the soil, are those like cover cropping and having perennial crops, and to some extent crop rotation, that increase the amount and diversity of roots in the soil. And this video should give you a pretty good idea of why that is. This is a soil box where I've compacted the lower area here and had grown some oats and radish in this box the year before. So you can really see now why having roots in the soil and keeping them there without disturbing them is a benefit to infiltration. And not only that, but like I said, soil organic matter, roots are 2 to 13 times more efficient at building soil organic matter pools than having above ground residue or plant matter. There's something about the roots, both in their composition and in their proximity to soil particles, that makes them that much better at building soil organic matter. And you can see that really well in this cross section here, where you can just see where there are roots and fungal hyphae that are mycorrhizal hyphae that are connected to the root, really just completely enmeshed in that soil matrix. And the other thing that those roots do is feed the microbial population with like root exudates and also sloughed off dead roots, and those microbes, once they die, will encrust soil particles and are actually a very important source of soil organic matter that then gets protected by aggregation, by that structure in those aggregates that form a nice crumbly structure. So I think we're running a bit low on time here, so I'll breeze through crop diversity. Just some really salient points is the resilience that we get from higher crop diversity. This is work that comes out of the Elora Research Station long-term rotation trials, and we can see that in a heavy drought year, a lot less corn yield is lost in a system where there are small grains with a red clover cover crop. Not only that, but there are benefits in terms of fertility. We can see that the corn, soy, wheat with underseeded red clover had much lower nitrogen requirements, much lower maximum economic rate of nitrogen for the corn year. And part of that is due to the fact that those soil organic nitrogen pools are built up so that you can see the flip side of that is when you add no nitrogen, you're getting a lot more yield out of those plots with corn, soy, wheat, red clover in rotation versus just the corn, continuous corn on the left. It's interesting to note that it's not just the red clover, that even having corn, soy, wheat improves the soil structure in such a way that those organic nitrogen pools are built, and the soil structure is such that our corn crop can actually access more of those soil resources. And last kind of interesting note for those of you who are maybe starting to hear about a carbon penalty from having too much residue, that having a more diverse rotation actually stimulates soil biological populations, soil microbes, into creating a greater diversity of enzymes that can actually break down tougher residue like corn or wheat residue more quickly than from soils that have a less diverse rotation. Continuous corn rotation being the one all the way at the bottom with the least amount of CO2 efflux, so less microbial decomposition compared to more diverse rotations with better ability to decompose those. And with that, just to reiterate those soil health principles: keeping it covered, minimizing disturbance, maximizing living roots, plant diversity, and integrating livestock or their poo as much as possible. Thanks.